the product of this matrix and this column vector or column matrix. First we write these in standard notation with the semicolons delineating the rows of the matrix. So the first row of this matrix contains 2 and 3. Second row contains 4 and -5. First row of this matrix contains just x. Second row contains just y. So this is the product of the two matrices, and when we multiply this out, we get, well, row times column, 2 times x, 3 times y. So we have 2 times x plus 3 times y. And then second row times the column, we have 4 times x minus 5 times y. Now there's another matrix product, and it's written out in similar notation, but it translates very easily into the matrix that you see here. This matrix multiplied by the column vector x, y, z. And when we multiply this out, what do we get? Well, row times column, 2x plus 3y minus 4z. 2x plus 3y minus 4z. 3x minus 2y plus 4z. 3x minus 2y plus 4z. 1, 1, 1 gives us just x, y, z, x plus y plus z. So the product of this matrix and this column is here. Now, if we take the matrix equation, the same matrices we have here, 2, 3, 4, -5 matrix multiplied by the xy column vector, the equation that says that that's equal to 32, the column vector 32, 18, that says then that since this product is 2x plus 3y, 4x minus 5y, that column vector that we get from this product is equal to the column vector 32, 18. Now that can only be so if whatever 2x plus 3y adds up to equals 32, and whatever 4x minus 5y adds up to equals 18, so that this matrix equation is equivalent to this system of linear equations. Similarly, this matrix equation is equivalent to, well, here's the product of the same two matrices, so that the first row is going to be 2x plus 3y minus 4z, and that's going to have to equal the first row of this matrix. And then the second row of the matrix we get here is 3x minus 2y plus 4z, and that should equal the second row of this column matrix, -3. And then the 1, 1, 1 gives us x plus y plus z. That's going to be the third row of our product matrix, as we can see over here, and that's going to equal the one that we have in the third position in this column vector or column matrix. So that this matrix equation is equivalent to this system of linear equations. So once more, this matrix equation is equivalent to this system of linear equations. This matrix equation up here is equivalent to this system of linear equations. And any system of linear equations where you have the same number of linear equations as you have variables can be translated into a matrix equation. If you had 4 equations and 4 unknowns, you could translate it into a 4 by 4 matrix multiplied by like x, y, z, w, or whatever your unknowns are, equal to a column of 4 numbers. Now where we're headed with this is to a solution of the system without writing out the system, without doing elimination, without doing a row reduction on the augmented matrix, using what we call the inverse matrix, the inverse of this matrix. If we multiply the inverse of this matrix by the matrix, and we get what's called the identity matrix, and that essentially, if we then multiply the inverse of the matrix by this column vector, the numbers that we get are going to match x and y, and those will be our solutions. Now we have to move on and talk about identity matrices and the process of inverting a matrix before we can talk about how to solve these equations using matrix methods.